Alright, in this video we're going to introduce 3.1, which is dealing with critical points. So this is the beginning of Chapter 3, and Chapter 3 has to deal all with applications of the first derivative and second derivative. So now that we've gone through and found all these derivatives through the chain rule and product rule, we're going to actually start doing a lot of stuff now that we find the derivative. So very first thing we'll start off with is a definition of what a critical point is. So the first thing is that f has to be defined, so there has to be a point on the graph. We're going to call it f of c, and then x equal to c is a critical point if one of two things are true. It's going to be a critical point is if the derivative equals 0 at that point, or if the function is not differentiable at x equal to c, meaning that the derivative does not exist at c. So we're going to look to see where the derivative equals 0, or if the derivative doesn't exist at a point, then it's going to be considered a critical point. And the first example is graphically how we could determine critical points. So I'll give you a moment to pause it and copy these graphs into your notes. So based on the definition, we're looking at where the derivative is equal to 0. Derivative equal to 0 means that the slope is equal to 0. And for something to have a 0 slope, that means basically it has to be a horizontal. So if I'm traveling up this way, my slope's going to be 0 at this point, and if I travel on this way, it would also be 0 at this point. So you can think of it simply as the derivative is going to equal 0 whenever there's a maximum or whenever there's a minimum in the graph. So for the first one, we can say that the critical point would be at x equal to -1 because it's a maximum, and the derivative would be 0 at that point. Also at x equal to +1, there's also a minimum, which would make a horizontal slope, which also would make the derivative 0. And then based on the second half of the critical point definition, 2 is going to be a critical point because there's a kink right there. So at 2, there's a kink, which also makes the function not differentiable. So these two are points where the derivative is equal to 0. And this last one is where the derivative does not exist due to the kink. Alright, now the second graph, similarly at -1 there's a kink. So x equal to -1, you would say that f prime does not exist due to a kink. And also at x equal to +1, because if you travel along this way, at 1 there's a vertical tangent, which also would make it not differentiable. So x equal to 1 is also a critical point. Derivative does not exist. You would say a vertical tangent line. And based on the definition of there being a minimum at x equal to +2 would also be a critical point. So you would say that derivative at x equal to 2 is equal to 0. Now if you head over to 3, there's a vertical asymptote on the actual graph of the function. And that's not going to really play into there being a critical point, because the first part says that it has to be defined. And since functions are not defined along an asymptote, we're not even going to consider it. So that's why the vertical asymptote wouldn't come into play. Alright, second example is actually looking at a function. So we're given f of x equal to this. And to find my critical point, I'm just going to be looking for where the derivative is basically equal to 0. The first thing I do is I find f prime using just the regular power rules. For each one of these terms, this is going to be 12x squared. This is going to be a minus 18x. This is going to be a minus 12. And I go ahead and set this equal to 0. And I have a common term I could factor out of all of these, which is going to be 6. So if I take a 6 out, I'd be left with 2x squared minus 3x minus 2, which is a factorable quadratic. So I can put my two parentheses. This is going to be a 2x and x. This is going to be a 2 over here, 1 there. This is negative, this is positive. I'm still setting this equal to 0, so I solve each one of these. 2x plus 1 is equal to 0. X minus 2 is equal to 0. So solving these two, positive 2 is a critical point, and negative 1/2 is a critical point. And then we can verify this graphically. So we said 2 and negative 1/2 were critical points. So this is the actual graph of f. So you can pause it and copy a small portion onto your graph, onto your notes. And you can see that positive 2, like we said, is a minimum. That's where the tangent line would be horizontal. And then also negative 1/2 is a maximum, which would cause a critical point at negative 1/2. And once you have this copied into your notes, you can draw the graph of the derivative in a kind of dotted form and kind of see that it matches up with the derivative equal to 0, where there's a minimum, and also the derivative equal to 0, where there's a maximum. So what you can do is, once you have f copied into your notes, you can make a little dotted trace of the derivative on the same axis to see that they in fact match up where there's zeros and when there's a maximum and minimum. Got one more example for this video. It's going to be let g of x equal this function. We're going to find the critical points to that. So before I find my derivative, I want to rewrite this so I can see what exponents this is being raised to. So it's x squared minus x. It's the cube root, so it's going to be raised to the 1/3. So to find this derivative, I have to use the chain rule. So my g prime of x is going to be the power rule. I drop the 1/3 in front, subtract the power by 1. So 1/3 minus 1 is negative 2/3. Keep the inside the same. And then the chain rule says multiply by the derivative of this, which is going to be a 2x minus 1. Simplifying this a bit, I can, this is going to be in the denominator because it's a negative exponent. So it's going to be 2x minus 1. This is going to be 1/3 in the bottom. It's going to be x squared minus x raised to the 2/3. If it's negative, I can bring it down in the denominator and make it positive. And I'm going to go ahead and set this equal to 0. Now, when I set this equal to 0, I'm going to go ahead and solve only the numerator. So it's going to be 2x minus 1 is equal to 0, which is going to give me 2x equal to 1, so x is equal to 1/2. This is the case where g prime of x is equal to 0. So that's my one critical point. I also have to consider in the denominator where the derivative doesn't exist. Because if the derivative doesn't exist, that's the second half of a critical point definition. So if I ever get the denominator to equal 0, that's where the definition of the derivative would not be defined. So I'm going to solve the denominator also set equal to 0. So 3 x squared minus x to the 2 over 3. I can divide the 3 over, so 3 divided by 3, it cancels off. It's going to be x squared minus x to the 2 over 3. This remains at 0. Then I can raise both sides to the reciprocal of this, so that raises this to the 3 over 2, raise this to the 3 over 2. That's going to undo this, and that still remains 0 on this side. So it's going to be x squared minus x. This is now a factorable quadratic again, so it's going to be x minus 1 is equal to 0. So x is equal to 0, x minus 1. So 1 is a critical point, 0 is a critical point, and then we also said 1/2 is a critical point. And then looking at the graph of this, we can see that at 1/2 it's a minimum, and then at 0 and 1 the derivative would be undefined because at both of those points there's vertical tangents. So you can copy this also into your notes, and then we can kind of match up the derivative with the blue dotted to indicate that there's a minimum right over here. That's where it's crossing the x-axis, and also at 1 it's a vertical tangent, and you can see that the derivative is undefined because it has a vertical asymptote. And same thing with that 0, the function is undefined and there's a vertical asymptote in the derivative, making it undefined. And that's it for this video.